Hello, everyone. Good afternoon. Welcome to today's webinar, and thank you very much for coming today. My name is Tohru Ikeguchi from Tokyo University of Science, and today I will talk about analysis of complex dynamical behavior as a temporal network. So if you have any questions, please send them through the chat box. And after finishing the talk, I will try to check them and answer them. Okay, so let's get started. This slide shows the contents of what I plan to talk today. As the title, Analysis of Complex Dynamical Behavior as a Temporal Network, means that today I'm mainly talk about how to analyze temporal networks. But before going to that, I would like to introduce a non-temporal, that is so-called static network and its analysis as a fundamental part of today's talk. And the corresponding contents of this part will be about items 1 through 9. And after that, we will move on to the contents of how to analyze temporal networks. And we will start with what is the temporal networks and why we will analyze complex phenomena as a temporal network by discussing the importance of analyzing the temporal information. And on the analysis method of temporal networks, there are various analysis methods, but in today's talk, I will introduce the spectral distance, which is used to measure internetwork distances and its applications. I will talk about two applications to evaluate the dynamical behavior of the networks in the real world. Okay, so let's start with the so-called small world phenomenon. Please take a look at the slide. This is the opening sentences of an article written by American psychologist Stanley Milgram. The title is The Small World Problem, published in Psychology in 1967. So let's take a look at the contents. So Fred Jones of Peoria, sitting in a sidewalk cafe in Tunisia and needing a light for his cigarette, and asked the man at the next table for a match. They fall into conversation. The stranger is an Englishman who, it turns out, spent several months in Detroit. I know it's a foolish question, said Jones, but do you by any chance know a fellow named Ben Arcadian? He is an old friend of mine, manages a chain of supermarkets in Detroit. Arcadian, the Englishman mutters. Why, upon my soul, I believe I do. Small chap, very energetic, raised merry hell with the factory over a shipment of defective bottle caps. No kidding, Jones exclaims, and amazed. God Lord, it's a small world, isn't it? Let me illustrate what I just said. There are three characters in this story: Fred Jones, an Englishman, and Ben Arcadian. Fred Jones happens to be talking with this Englishman in a cafe of Tunisia. So Fred Jones and the Englishman became acquainted. On the other hand, Fred Jones was already acquainted with Ben Arcadian. So thinking it was unlikely, Fred Jones asked if the Englishman and Ben Arcadian was acquainted, and they were. So Fred Jones and this Englishman astonished, and they say it's a small world. And in fact, I think that you all have experienced something like this. When A and B and A and C are acquaintances, B and C are often acquaintances as well. So this psychologist, American psychologist Stanley Milgram, tried to confirm such a small world phenomena by an experiment. First, Milgram hypothesized that if our world is a so-called network of friendship, then our world is in some sense small. So one of the simplest ways of formulating the small world problem is what is the probability that any two people are selected arbitrarily from a large population, for example, the United States, they will know each other. So in the Milgram's experiment, totally 296 arbitrary individuals selected in Nebraska and Boston, and they are asked to generate acquaintance change to a target person in Massachusetts. So here is an overview of the Milgram's experiment. First, a studying person and the target person are selected. If the selected starting person knows the target person directly, she can send a letter to the target person. On the other hand, if the starting person does not know the target person directly, probably, which is often the case, then instead of contacting the target person directly, the letter is sent to someone who seems to know the target person better than the studying person does. So the next person to whom the letter is sent from the studying person now will respond in the same way. That is, if you know the target person, you can send a letter directly to the target person. But if you do not know the target person directly, you send the letter to someone who seems to know the target person better than you do. And the definition of knowing here is that you call each other by your first name. So now the letter is sent to finally the target person now. So how about the total results of this Milgram's experiment? Let me explain the results. This is the result. The horizontal axis of the graph is the number of persons needed to reach a target person, and the vertical axis is the number of letters that reached the target person. So total number of letters sent in this experiment is 64, as shown here. The number of steps by which these were delivered to the target person, the result is quite surprising. As you can see, the most frequent number is 6. So the population of the United States in 1960s to 70s was just under 200 million. So compared to this population, a letter can reach the target person only in 6 steps. This result was received with very so-called very big surprise. And as a result, the number 6 degrees of separation 6, became known as the 6 degrees of separation now. Actually, this 6 degree of separation manifests itself in a variety of places after this experiment. For example, on the left is a 6 degrees of separation, which was written by American playwright John Gale, and that premiered in 1990. On the other hand, on the right, 6 degrees of separation, which is a 1993 American comedy drama film, and of course adapted from John Gale's play. And this film was starred by Stockard Channing, Donald Sutherland, and Will Smith. So these phenomena, yes, these results are very accepted, very great surprise, yes. Of course, however, there are some criticism of the Turbers-Milgram's experiment. For example, the number of letters actually delivered to the studying from the studying person to the target person may be very small. In the experiment, the number of letters received from 296 studying persons was 64. So the similar experiment was conducted by his group to overcome these issues. It was 23. In their experiment, they did not use letters, but emails. In this experiment, more than 60,000 email users are selected, and they forwarded the email message to 18 target persons in 13 countries. And after analyzing the data obtained from the experiment, they conducted that the average number of steps was between 5 and 7. And they also conclude that although such a global social network are in principle searchable, actual success depends sensitively on individual incentives. So here is another example of small world phenomena. This is a sort of game, which is called the Kevin Bacon game. The Kevin Bacon game is a game in which one selects an actor and repeats the process of connecting the actors to another actor through the films in which both these actors start together in order to find the shortest path that leads to the American actor Kevin Bacon. And the game is based on the assumption that anyone involved in the Hollywood film industry can be connected with Kevin Bacon, through the films in which they are starred by following a 6-step process. In this game, each actor is evaluated by their own Kevin Bacon number. So let me define the Kevin Bacon number in this game. First, the Kevin Bacon number of Kevin Bacon is 0. And the next, the Kevin Bacon numbers of actors who have already played with Kevin Bacon is 1. Next, the Kevin Bacon's numbers for the actors who have starred an actor who has already starred with Kevin Bacon is 2. Okay, so this is how we can define the Kevin Bacon number. So now let's take a quiz. Given an actor or actress, how many Kevin Bacon number do they have? To answer this quiz, you can use this page, the Oracle of Bacon. The URL of this page is oracleofbacon.com. When you visit this page, you will see a top page like this. And as you can see here, you can find the link from Kevin Bacon to someone whom you are interested in. In the next slide, I will show some actual results. This page shows the result for a young Japanese actress, Kanna Hashimoto. So the first Kanna Hashimoto and Takeo Nakahara co-starred in the movie Assassination Classroom Graduation, and Takeo Nakahara co-starred in Rainfall with Gary Oldman. Gary Oldman co-starred with Kevin Bacon in the movie Criminal Law. So the result indicates that Kanna Hashimoto's Kevin Bacon number is 3. Next, I will show the result for Yui Aragaki, another Japanese actress. First, Yui Aragaki co-starred with Ryosei Tayama in the movie Ranma 1/2, and Ryosei Tayama has acted in Rainfalls with Gary Oldman, and Gary Oldman co-starred with Kevin Bacon and JFK. So Yui Aragaki also has the Kevin Bacon number 3. The last example is Ryoko Hirosue. First, she was in a movie called Bokyo, and she co-starred with Keiichi Shina in the movie Bokyo. So secondly, Ryosei Tayama is in the movie Rainfall with Keiichi Shina, and he has starred in a movie called The Outsider, Laurie Cochrane. And Laurie Cochrane has starred in the film of Outsider, and Laurie Cochrane and Kevin Bacon were in a movie called Black Mass. So she also has, Ryoko Hirose also has the Kevin Bacon number 3. So these results for the 3 actresses are shown in these 3 slides. You can see that the number of small steps leads to Kevin Bacon, regardless of the age of these actresses. Actually, this table shows the distribution of the Kevin Bacon numbers. The data are collected on July 27th, 2023. The most left column of this table shows the Bacon numbers, and the next column shows the frequency of actors or actresses for each Bacon number. The third column shows the cumulative frequency. First, the Kevin Bacon, Kevin Bacon number 0 is Kevin Bacon himself. So Kevin Bacon's Bacon number is 0. Then the corresponding number of actors is 1. Next, we can see that there are 2,072 actors whose Bacon number is 1. That the number of actors with Bacon number up to 1 is 2,073, including Kevin Bacon, whose Bacon number is 0. And third, there are 214,165 actors with Kevin Bacon number 2. Thus, the cumulative number of actors up to Bacon number 2 is 216,238. Repeating this process, we can obtain this table. And from this frequency histogram, we can calculate the average Kevin Bacon number, which is shown in the lower left corner. The average value is 3.0096, which is by far the smallest compared to the actual total number of actors of 1,185,479. So I have introduced 3 examples of the small world problem. The first one is Travers and Milgram's experiment using letter chain. The second one is the Dodds group's email experiment. And the third one is Kevin Bacon game. So these examples show that the various networks in the real world are so small, they are small world network. In fact, the first example, the letter chain experiment show 6 degrees of separation. And the second one, the email experiment, had the 5 to 7 steps. And the third example, the average Kevin Bacon number was 3.069. So, however, these numbers 6 or 5 to 7 or 3.069 are not important. The important point is that these numbers are significantly smaller than the number of vertices of the network. Actually, for example, in case of the World Wide Web, it said that the 19 steps is enough to reach every pages Actually, the number of total web page is approximately 1.9 billion. And another important point is that it doesn't matter who is the center. In case of Kevin Bacon game, the same results are obtained. Even if you consider, for example, Marilyn Monroe or Audrey Hepburn as a center who have already passed away. The same result, same tendency can be obtained by setting the Marilyn Monroe and the Audrey Hepburn as a center, and you can get the Marilyn Monroe number or the Audrey Hepburn number. So far, actually, we have discussed the Milgram experiment, the email experiment, the Kevin Bacon game. But these are only small examples of friendships and active co-starring relationships. But actually, we are surrounded by many other types of connections or networks. For example, the internet, World Wide Web, or infectious disease or viruses, trends, rumors, air network, road network, and rail networks, and the power grids of food chain, neural networks, language, and human contacts. So as you know, the graph theory is a theory for analyzing these connections or graph or networks, which is the start point for complex network theory or network science as we know it today. It is said that the graph theory began with the Königsberg Bridge problem solved by Euler in 1736. After 1736, various results were obtained and accumulated through the work of, for example, Cauchy, Middleton, Cayley, Kirchhoff, and so on. And in the middle of the 20th century, two mathematicians, Erdos and Rennie, made progress, for example, in the study of random networks. Further, at the end of the 20th century, a new field of network theory, which is now called complex network theory or network science, began. These were started by the following two famous studies. The first one is the Watson-Strogatz work on the small world network. And the second one is the Barabasi and Albert's work on scale-free network. From the next slide, I will briefly explain how these two networks, the small world network and the scale-free network, are characterized. These are basic indices used in the field of newly emerging network science fields. So among these, the small world network is characterized by the first two indices, the average path length and the clustering coefficient. And the scale-free network is characterized by the degree and its distributions. So let me explain from the average path length. First, let's look at the average path length between vertices is the so-called the shortest distance between two vertices. For example, Vi and Vj. In the case of the, of course, undirected graph, it is a minimum number of edges between two vertices, Vi and Vj. So let the sub ij be the shortest distance between vertex Vi and vertex Vj. Then average path length L is expressed by this expression, middle center of the slide. Then, of course, the average path length between vertices can be easily calculated by, for example, the Dijkstra method. So in case of a very simple example of the at the right, shown in the at the right, the average path length L is 7 divided by 6. Now let's check up the clustering coefficient. The clustering coefficient is so-called a measure for evaluating how many triangles exist, for example, just around a given vertex pi. Please see the vertex vi in the simple graph on the right. For example, a red triangle structures like this exist. Of course, there are other such triangles just on the vertex vi. Of course, these three triangles were not the only triangles that exist when vi is considered as a center. So we calculate how many triangles exist just around the given vertex vi. First, to form a triangle centered on vi, we count the number of adjacent vertices of vi, because these edges from vertex vi are necessary to form a triangular structure centered on vertex vi. In case of the graph on the right, the number of adjacent vertices is 6. So which means that at most 15 triangles, 15 triangles can be formed. On the other hand, only 8 of these triangles are actually exist or formed in this example. Therefore, we defined 8 divided by 15 as the clustering coefficient of vertex vi. And finally, the clustering coefficient of the network is the average of the CI. And Watson and Strogatz measure the clustering coefficient and the average path lengths for various real-world networks. The results are summarized in this table. In this table, the left column indicates the network. From top to bottom, USAI network, C. elegans, the neural network of an animal, which is called C. elegans, and in the college football matchup chart, a network dolphin relationship in an aquarium, the power grid network, the relationships of jazz musicians who performed together on the same stage, the relationships of a character graph, and the adjacency of words in some language, and the adjacency, adjacency of some language. Actually, it was in English. And in the table, small n is the number of vertices in the network. And the number of vertices and edges differs among networks. Therefore, a sort of normalization is required when we are discussing the average path lengths and the clustering coefficient between different networks. So therefore, we consider the first, if the network under the analysis is a small world, the average path lengths are expected to be so small. So, and this phenomena is also holds for random networks, the same as random networks. On the other hand, if the network under analysis is a small world, the clustering coefficients are expected to be high. And this is different for the random networks because random networks has a very small clustering coefficient. So we calculate the clustering coefficient and the average path lengths of the origin network. But evaluating the difference between these networks, we normalize these clustering coefficient C sub O and the average path lengths of L of O are normalized by the clustering coefficients and the average path lengths of the corresponding randomized networks. And we calculate the ratio of CO to LO, CO to CR, and LO to LR, and we can evaluate the small world properties of these real networks. Actually, we can see that the ratio of CO to CR is very large, and LO to LR is approximately unity. So we can conclude that these networks are very so-called small, has a small world properties. Then Watts and Strogatz propose a model of small world phenomena. This is an overview of the small world network model proposed by Watts and Strogatz. They show that by transforming the regular network, a network with small world characteristics, small world properties can be created. Example, actually, specifically, we use an idea of so-called the rewiring edges with some probability P. So this probability P is introduced as a parameter that determines whether or not to rewire each edge in the regular network. For example, if P equals to 0, no edges are rewired, but if P equals to 1, all edges are rewired. So when the rewiring probability P equals 0, the network is regular. And in this case, the clustering coefficients are large, and the average path lengths are also long. On the other hand, when the rewiring probability is 1, it corresponds to a random network, and which is in which the clustering coefficient is small and the average path length is small. So therefore, if the value of P is intermediate value, a small world network with large clustering coefficient and the small average path length can be realized. So this is the result for the model of the small world network. And this figure shows the result of calculating the clustering coefficient C and the average path length L from a regular network with increasing rewiring probability. So the horizontal axis of this figure shows the so-called rewiring probability P, and the vertical axis shows the clustering coefficient C of P and the average path lengths of L of P. But these C of P and L of P are normalized by the clustering coefficient of C of 0 and L of 0 when P equals 0 respectively. First, the values of C of P divided by C of 0 and L of P divided by L of 0 around P equals 0 are very high, very large value, almost unity. And which indicates that the characteristics of a regular network, of course. On the other hand, the values of C of P divided by C of 0 and L of P divided by C of L of 0 at P equal 1 are both small, which indicates that this is the characteristics of a random network. And for intermediate values of P, for example, P equals to 0.01, the value of C of P divided by C of 0 remains high value, while the value of L of P divided by L of 0 is very small, indicating that the small world phenomena is reproduced. So this is a so-called small world network model proposed by Watts and Strogatz in 1998, which is the start point of the complex network theory. Actually, this small network model can explain small world phenomena observed in the real world networks. However, there is also a problem. We should check the degree distribution. This slide shows the degree distributions of the small world network model for various rewiring probabilities P Yes, so degree distributions are shown here. From left to right, the rewiring probability P is 0.001 and 0.0056, 0.017, and 0.056, and the finally P goes set to 0.562. And the corresponding degree distributions are shown in the slide. In case of the P goes to 0.001 in the green case, the degree distribution has a strong peak. And as the rewiring probability increases, the degree distribution gradually extends horizontally, and it becomes a so-called bell-shaped distribution. And the reason why the degree distributions of the Watt-Strogatz model is that the initial graph, the starting point, or in case that P equals 0, is a so-called regular graph, or a so-called ring lattice. Then these results show that the degree distributions of the Watt-Strogatz model has of course, nearly bell-shaped shapes. Then what is the degree distributions of the actual network? To think this point, let me show you some structural characteristics of real network, or the visualization of the real network. For example, this is an American network chart, aeronautical network charts of an airline company in the United States. In this figure, we can see that so-called hub airports, or airports which has many airline routes. You can see the so-called hub ports in the west coast or middle of the mainland of the United States and the east coast. Yes, these hub airports have the many airlines. And the next example is the visualization of the internet connection. Again, we can see that connections are concentrated on certain devices, which can be called hub. This slide shows the connections between the pages of some website. You can see that some of these pages have a large numbers of links. This is a high school friendship network. It shows a variety of patterns, from those who have many friends to those who have only a few. This is a network interactions between major characters in the novel Les Miserables by Victor Hugo. Although this result shows the existence of communities, for example, but we can see some vertices or some characters who has large degrees. This graph shows the transmission of tuberculosis. You can see that the black vertices have very large edges to many other peoples. This graph comes from the risk network structure of persons with HIV infection during its early epidemic phases in Colorado Springs, United States. It uses analysis of community-wide HIV/AIDS contact tracing records of sexual and or injecting drug partners from it was 1985 to 1990 or so. We can see that some vertices have a very large degree. So these several real networks have a different characteristics than the model of the small network. As shown in this slide of lower left figures, there are a small number of degrees whose frequency is non-zero, and the value of these degrees are not so small. Actually, they are large. A vertex with such a large degree value is often called a hub vertex. So what is even more interesting is that when this degree distribution is plotted on a so-called log-log graph, you can see a straight line. You can observe a straight line. Yes, straight line appears as shown in the right bottom. The appearance of such a straight line on the log-log plot means that the degree distribution P of k has a form k to the power of minus gamma. So this is another typical characteristics of the real networks. And let's look at the result for an actual network of the result of the degree distributions for the actual networks. Here you can see the results. Now the A is the network of the actor co-starring relationship, and the B is the World Wide Web, and C is the power grid data. In this table, you will find the number of vertices and the average degree and the value of gamma. Please note that the figure above, you can see that the straight line, yes, straight line for A, straight line for data B, and straight line for C. You can see these straight line appears when the degree distributions are plotted on a log-log graph. And the result of the obtaining the slopes of the corresponding linear part is shown in the table. The values of the gamma are 2.3, 2.1, and 4 respectively. So this is the result shown by the Barabash and Albert in 1999, and which is also surprised many people because many real networks has this kind of scale-free characters. So what kind of mathematics mechanism is needed for such an degree distribution to become a power law? So how can we reproduce such a scale-free structure? So this is the model proposed by Barabashi and Albert in 1999. And this model has important two characteristics. The first one, it is a growth of the network, which means that the new vertices are usually connect to an already existing network. So the network grows. For example, when we get a new computer or a new smartphone, and so on, we usually connect them to the internet. So the second characteristics is that these newly added vertices has a tendency to connect to the higher degree vertices in the existing networks. This feature can be easily understood if, for example, when you create a web page, probably you write some new web page with HTML, and you will write also the links to other pages from your page to the very famous page, Yahoo or Google, and so on. And this property, Barabashi, Albert, they call it, this property is a preferential attachment. So their model, Barabashi and Albert's model, has these, it's 4 steps. First, initial network is a complete graph. This is prepared, and the number of vertices is m naught. And at the new vertex with m edges, this corresponds to the growth. And the vertex to which the new edges is connected is determined by the following rule. The first one is, let K be the degree of an existing network VI, and degree, yes, ki. So the probability that an edge of the new vertex connects to the existing vertex bi is determined by the following equation. P of vi is proportional to ki, and this pi is a probability that the new vertex is connected to the vertex bi, which has a degree of ki. So to make it the probability, so we just denormalized or divided ki is divided by the total sum of the total degrees. So at t equals 0, there is a complete graph example, in this case for vertices, and the new vertices with 3 edges is coming now, and the vertex in the existing network acquires the edge of the new vertex with probability proportional to its degree. Of course, at t equals 0, this is a complete graph, so the probabilities are equal, but let's say that this is the case, and at the next t equal 1, new vertex again arrives. And the higher the degree of the 5 vertices in the existing network, the higher the chance, yes, of acquiring these 3 edges. Now, networks look like this is obtained. And in the following t, the almost the same process is repeated, and we can get the existing growing networks like this. So by providing these 2 features of growth and preferential attachment, Barabashi and Albert show that the power law appears in the degree distribution. And please look at the left figure. You can see both the horizontal and the vertex, both in A is both horizontal and vertical axes are logarithmic. On the right, only the vertical axis is the logarithmic. So left figure shows the case with growth and preferential attachment is introduced, and the right figure shows the case only the growth is introduced. So you can see that if you introduce 2 properties, growth and preferential attachment on the left, both logarithmic graphs are straight lines, indicates that P of k has a scale-free property. So starting with a smaller network paper published in the 1998 and the scale-free network paper published in 1999. So various methods for analyzing networks have been proposed. So, but although I will not go into further details in today's talk to these properties, but there have been many proposals for network analysis indices, for example, so-called now centrality or community detections and so on. But today's talk, I would like to go to the so-called the property that the real networks have. Yes, real networks has are not static one, but they are very, very dynamic. So as one of the directions for the complex network theory, analysis of so-called dynamical network or temporal network, in which the network state change with time, it is also important. And actually many research is now conducted now. So from now, I'd like to talk and discuss about the temporal network analysis. So as I have just mentioned, the temporal network is a network whose state changes over time. For example, in this figure, the state of the network at time t changes at time t plus 1. In this way, a temporal network is a network whose state changes. And examples of the temporal network are, for example, person-to-person contact, human contact, neural networks, and the telephone communication networks, email networks, or protein-protein interaction networks. And in today's talk, I will introduce two types of data. The first one is human contact data, and the second one is usage history data of a bike sharing system. So before going to the concrete example, I'd like to discuss about the importance of the temporal information. So why temporal information is so important? So that's some temporal information allows us to better understand the characteristics of the network. For example, please consider the figure on the left in the slide. The left figure shows a schematic representation of a record of contacts between 5 people, A, B, C, D, and E. So the vertical lines or vertical curves represent contacts. So for example, contacts could be a conversation or so. So in the left figure, as the first event at time t1, so at time t1, A and B contacted. In the second event at time t2, B and C contacted. And in the third event, D and E have a contact at time t3. And the fourth event at time t4, B and E have a conversation. And the next event at time t5, C and D had a contact. And the last event at time t6, B and D had a conversation. Suppose that if some information is sent from A, in this case, sorry, oh, mistake, oops. In this case, some information is sent from A, and this information can be transmitted from A to B, and B to C, and C to D, and D to E. On the other hand, if some different information is sent from E, for example, in this case, the information is transmitted from E, so E to D, and D to C, and E to B, but in this case, A cannot receive this information. So now let's think about a network in which the contacts are superimposed, not introducing the temporal information. Such a network is often called an aggregated network, which is shown on the right. In this network, vertex B plays the role of a hub. So in this aggregated network, all vertices are connected through the vertex B. So any information can be transmitted to all vertices. So these two examples are very different. So on the left example, in some case, for example, in this case, A cannot receive the information. But on the right example, it said that all vertices can receive the information. These differences indicate that it is important to consider the so-called temporal information, or analyze these networks as a temporal networks. So now how we analyze the data as a temporal network. Please let me explain how to do that. Now I show you the temporal evolution of the networks in this slide. So one of the ways to analyze the data as a temporal network is to look at the ICE network and the indicators that characterize this and discussed in the as the first half of today's talk, how these indicators or change over time. For example, we can measure the clustering coefficient of network GI or clustering coefficient of network GJ. And we can discuss how these clustering coefficient change over time. However, we do not discuss about in this analysis method. We will discuss the how to evaluate the dynamics of the temporal networks by measuring the distance between the network GI and the network GJ. So if we can measure the distance between the network GI and GJ, it's represent the dynamics of the network. So as you can see in this slide, we will consider, yes, how to analyze the dynamics of the temporal network by calculating the distance between the states of the network at each time window. And we evaluate this temporal evolution of this different distances by time evolution. So let me explain how to analyze the temporal network today's talk. So first, to obtain the temporal network data, yes, we divided the data into several time windows as shown in the top of this slide. In this slide, the temporal time window, the temporal width of each time is described by tau. Then the ith network after this division is considered to be the state value of a time I. So for each state, we compute the first the distance between two states. So we can compute the distance matrix between the network in the ICE window and the network in the JS window using the distances between graphs. So horizontal axis and the vertical axis of distance matrix can be thought of as a time indices. Next, we time evolution variation between the state values, at least the time series signals, is obtained by applying the CMDS, classical multidimensional scaling. Yes, by applying the classical multidimensional scaling to this distance matrix, we obtain the so-called low-dimensional time series signals. So finally, the third part, from this obtained time series signal, we reconstruct so-called attractor from transforming the obtained time series signal into time-delayed coordinate system to determine how dynamically the network are changed. So first, let me explain the method 1, calculating the distance between graphs from the next slide. I'm sorry, before going to that, I'd like to introduce what kind of temporal networks we used. Actually, I've already explained. We used two kinds of data sets. The first temporal network we used come from the human contact data. And actually, we use the data set or in the, now I shown the web page, so-called social patterns website. In this website, 15 data sets are recorded, and you can use them as an analysis of the temporal network. And I will show you some results of the contact data from this website. So first, I'd like to introduce the analysis results of the human contact data. So actually, data collection uses an active radio frequency identification device, so-called RFID device, embedded in the badge. And these badges are weared by the people. And this RFID device exchanges the very ultra-low power radio packets in a peer-to-peer fashion. So we can get some so-called contact data, relatively very high resolutions. So the data measured in this manner is shown in the upper right corner of this slide. The first column shows the time, and it is sampled in every 20 seconds. And the second and the third columns show who made contact with whom at each time t. For example, please show the right on the upper side. The first row of the upper right data is described 25 and 7, which means that contacts by the person 5 and person 7 were made at during the first period. And the second and the third lines are, for example, 45, 7 and the 45, 4, 6, yes. So it indicates that the person 5 and 7 contacts and the person 4 and 6 were contact. Then these contacts are made during the next period. Next means in the case 40. So from this contact information, the network shown in below, for example, at time equal 20, an edge is placed between vertices 5 and 7, and at time t equals 40, an edge is placed between vertices 5 and 7. And between vertices 4 and 6, I forget. So in this way, a temporal network is obtained. So next, how we measure the distance between graphs. So please show this slide. On the top of the slide, we have already had a temporal network divided by the contact data. So let us assume that yes, we have already had contact data, and it is already divided into the temporal windows. And let the I is the ith network, and the j is the network of the jth time window. For example, in the ith window, in this example, contact by vertex 1 and vertex 2 is made once, and contact by vertex 1 and vertex 3 is made twice. On the other hand, in the jth window, vertex 1 and vertex 4 contacts. So we can then create adjacency matrices AI and AJ for the network GI and GJ, where the number of contacts is weighted by the number of contacts. For example, in the adjacency matrix AI represents one contact between persons 1 and 2, and 2 contacts between persons 1 and 3. So next, we create from this information, create the degree matrices, DI and DJ, whose diagonal lines are degree of vertices. And then this formula is used to compute so-called Laplacian matrix L. And the L prime is a normalized Laplacian matrix L prime. And from these normalized Laplacian matrices, we can obtain the eigenvalues of lambda I and lambda j. From these eigenvalue vectors, information of eigenvalue vectors, we obtain the so-called normalized spectral distance d of ij shown in this slide. And we use this distance as the distance between the two graphs. Of course, we can use, we have another definition of the distance, but we use, today's talk, I will only show the results of using this spectral distance. So next, the relationship between the state value is analyzed by applying the classical multidimensional scaling C and DS to the obtain the distance matrix. Yes. CMDS is a method to reconstruct the distance relationship of, in this case, network in lower dimensions than the original dimension, by preserving the distance relationships of the input distance matrix. That is, the networks are rearranged so that the distances are smaller. Objects in smaller states are closer to each other, and objects in the different states are farther away from each other. So this allows us to reveal temporal changes in the structure of the network behind the distance data. So in this talk, the sequence of eigenvectors corresponding to the maximum eigenvalues when CMDS is applied is treated as a one-dimensional state transition time series. So finally, we apply the delay coordinate method to the obtained one-dimensional time series data. We would like to discuss the temporal structure of the reconstructed attractor obtained by transforming this one-dimensional time series data into an m-dimensional reconstructed state space, as shown here, V of t. This reconstruction attractor is technique used in nonlinear and chaotic time series analysis. And we also, try to evaluate the recurrence structure of the reconstruct the state space. So we, as I have already explained, we use the data from the social patterns website. And from the 15 data, today we only show the two cases. The first one is the contact data of a primary school, and the second one is contact data of the high school. So this is one of the results for the primary school contact data. In this figure, the upper figures show the distance matrices, and the lower figure shows the time series x of y obtained by applying the CMDS to this distance matrix, and the time series S. And the red time series is the time series of the number of contacts, the variation of the number of contacts temporarily. So this is a result for the time window. Okay, so 300s and 600s. So we can see that the several variations of the temporal evolutions and the, actually, this is a 900 result and 1200 second results. But, oh, sorry. Yes, actually, we analyzed how the application of our method to the contact data. This information is different from the temporal change of the variation of the number of contacts. So we plot the correlation diagrams between the time series of the number of contacts, C of I, this is red time series, and the correlation diagram between this CI and the XI, the time series obtained from the CMDS, X of I, this is a blue line. So horizontal axis of the correlation diagrams is the number of contacts, red time series, and the vertical axis is the time series obtained by applying the CMDS to the distance matrix. This is a blue time series. From these figures, we can see that the correlation between the time series of the number of contacts and the time series obtained from CMDS is very low. For example, in case of tau equals to 900, correlation is almost zero. So, which means that we can obtain a very different information from in case of applying CMDS. Yes, the time series obtained from CMDS can capture the different characteristics of the network that are not that cannot be seen from the number of contacts. And we can also show a so-called recurrence structures of the reconstructed time series of the reconstructed state space. This is obtained from the time series X of Y, and you can see that there are certain recursive structures of the trajectories. So this result indicates that there is a hidden recurrence dynamics in the primary school contact data. And this is a high school data, but I'd like to skip because I do not have enough time. So this is a correlation diagram. And different from the primary school data, for the high school data has relatively high correlations. But it also has a recursive structures, as is the same with the primary school data. So let me go to the second analysis part of this is the bike sharing system data analysis. So bike sharing systems are attracting attention as one of the type of transportation system which offers greater convenience than the conventional public transportation systems. So in the bike sharing systems, multiple ports and bicycles are installed throughout the city. And you can rent and return the bicycles in a different port, in a various ports. Actually, and in Japan, for example, Docomo Bike Share or Haro Cycling or Loop are in operation now. So we use the temporal usage history of bike sharing system data as a temporal network. So the first, we get the user history data of some BSS systems. And these data are divided into a certain temporal period. In this case, you can see that the temporal duration is 1 day. So the day K has a network GK, and day L is corresponding to the network GL. So actually, the user history data of the BSS system records at which port a user rented a bicycle and at which port the user returned it. So these two ports can be considered as the vertices of the network. So start port and end port, these are vertices in the network. And if there is a bicycle usage, there exists the bicycle usage between these ports. So an edge is added in the network. And if there are more than one usage, the edges are, in this case, weighted. So you can obtain the network GK for day K and the network GA for day A. And you can calculate the distance DKL between GK and GL. So we applied the spectral distance to this DKL and applying the CMDS to this distance matrices and analyze the result. So these are the results for BSS in 4 US cities. From left to right, Washington, DC, New York, Boston, and Chicago. We used the data of August 2019, and we divided the data by day and created a network for each day. So on the top, we show the 4 distance matrices, but the size of this distance matrices is the 31 times 31. So first, we see that the pattern of the distance matrix is different for each city. And the next, on the third row, plots the red time series obtained by applying CMDS to the distance matrix, and the blue line time series, which are time series of the number of system users per day. So in these plots, weekends are marked with a light blue band. And we can see that these results also differ from city to city. In particular, for example, in Washington, DC, there is a difference between weekdays and weekends. While in the case of New York, the variation of the time series is almost flat, and no difference can be seen between weekdays and weekends. In addition, the correlation coefficients between these 2 time series are red and blue, as shown in the fourth row, and the highest value of correlation coefficient is just under 0.8 for Chicago, while it is almost 0 for Boston. So these results indicate that in Boston, actually in August 2019, the result obtained by the user history as a temporal network provide some special information that could not be obtained from the temporal change of the number of users. Actually, these results are for August 2019, but we are analyzing the result of other years and other months as well. So we can see some differences. Of course, before COVID-19, after that, the change of the dynamics, we can analyze these data, we can see or observe some different properties. But I will discuss, I will not discuss today. So please, if I can have any chance, I'd like to talk these results in future. Okay. So I'd like to summarize today's talk. First, I introduced non-temporal, the static network and its analysis as a fundamental part of today's main talk of the analysis of temporal network. And after that, we move on to the contents of how to analyze temporal networks. And we started with what is temporal networks and the importance of temporal information. And on the analysis method of the temporal networks, we introduced so-called spectral distance between 2 networks and analysis by the classical multidimensional scaling and the reconstruction of attractors to reveal the dynamic behavior of the temporal networks in the real world, to real world data, human contact data, and the bike sharing data. Okay. First, the NOLTA Society of the IEICE had already launched an electric journal, Nonlinear Theory and its Applications. And this journal is published quarterly, and it has been for 14 years since it was first published on the October 2010. And actually, we are very happy to announce that this June, the NOLTA journal received the impact factor. So once again, we'd like to express our gratitude to all those involved and ask for your continued support. Thank you very much. And these are call for papers for 2 special sections of NOLTA journal. The first one is special section on cellular dynamical systems, which will be issued on January 2024. and the deadline for your submission is very soon, July 31st. And second one is the section on recent progress in nonlinear theory and its applications, issued on the April 2024. And the deadline for the submission is this October 10th, 2023. Okay, finally, I'd like to thank everyone who come this seminar today. Thank you very much.